time dependent. But we should know the time dependent information are connected to the very fundamental and information, also represent the inner structure of the column. So that's how we admit to student. So because we have the connection from the macro or measurable quantity, and also those quantity connect with the structure of some of the inner property of the column. So we have a way to optimize our method. So that's the connection. So this is a very important factor. And we, okay, there's a chat. Hello, is that clear enough? Or a strong echo here. Okay, I don't know how to make it more clear. I can speak slowly. Okay. So we just learned some the process of the separation, and we so there to explain the extraction process or the partition process inside the column, and this way is usually some chemists like this way, and also this is also true. So and then this step also bring us from bring us to the measurable quantity, time and time dependent. So this is the thought. We have, considering we only have a single molecule, and we can consider so the left one, the blue part is the mobile phase, and the green part is stationary phase. So for the single molecule X, so in any short time interval, X is found in either phase 1 or phase 2 because there's only one, so they can only exist in one position. So, but we know so because the X have a certain property, so he should have some possibility, different possibility when it exists in the phase 1 or in phase 2. So if you measure the single X for a long time, you can count how many times it exists in this phase or how many times in the phase 2. So it's equivalent to another case. You have many X molecule, not the single molecule X, the many X. So in that way, they should also distribute they have the same distribution. Just like when you measure the X for the many times. If you have many X, they can, when they arrive the equilibrium state, they should have the same distribution, partition distribution, a certain distribution portion, and just like when you measure for the X for many times, because the partition property is determined when those two phases unchanged, they're only determined by the X itself. So in here we get the time. So when we consider from single molecule to the mass batch of molecule, we can build a rough relationship. So the portion when X exist the possibility existed in phase 1 or phase 2, the portion. So if the portion maybe this have one it appears in 2 times in phase 1, maybe this only appears 1 time, so the portion is 2. So this is the time portion. But if you have 3 molecules, the amount portion is 2/1. So if you only have 1 molecule, that one it appears 2 times and it appears 1 time here. So this is because of the basic principle of thermodynamics. So based on this thought, we can build the relationship from the quantity to connect the relationship of, from the quantity to the time quantity, the molecule number to the time. So why we connect to time? Because the spectrum is time dependent. So this is a rough relationship, and remember that we have the amount the portion the fraction of x is based on the life expression. So we can build the portion of x in a column also depend on their retention time portion, right? Time mobile over time mobile plus time in stationary. Right. So in the last class, we also so the time we can for a certain columns we can measure the mobile phase for a certain separation. We have a certain mobile phase velocity, and we based on the spectrum, you can see we can also measure the velocity of the analytes. I can go back to here, right? So this is the mobile phase velocity. This is the velocity of the solute for the, for example, maybe this one. So this is the solute retention time. So this is the unretained time. So we can also get the speed of the flow rate. So here, when we get this relationship, we found the retention factor can be represented in just use time. Retention time minus the unretained time over unretained time. So we can get, so we cannot measure the capital K, the coefficient, the distribution coefficient directly, but we can measure this one directly from the spectrum. So this is good enough. We don't need to measure the capital K. So that one for a certain column that's a constant. For a certain column and a certain analyze that's a constant. So we can get this one. And we should know the capital K. And this one works better when you analyze the spectrum. Yeah, so this is like explanation for how we get this relationship. Just use some simple mathematical transformation. So this is the target why we build such factors, why we introduce such concepts, and why this factor are so important. And this, So the meaning for the retention factor is it reveals the migration rate of a solute in graph column. So based on the definition of retention factor, we can know we can easily calculate the k, and we can know longer elution time with all the retention time corresponding to the higher k value. This is the definition, right? So we can get the k value easily from the spectrum. And this is another important parameter. It's called selectivity factor, alpha. This factor is used as a measure of the effectiveness of separation of two solutes. So the K, the retention factor, is just say one solute. So when we consider the two solutes, we need another factor called the alpha, the selectivity factor. So the definition is just the KB over KA. So this is definition, and obviously, so we can calculate the alpha of two peaks directly from the spectrum. So when you remember how the definition of K, it should be quite easy to remember alpha, but you should need to remember the sequence. Always the later one on the above B. This is a peak B, the B over A. So that's alpha should be always greater than or equal to 1. Right. So this is just based on the definition. So this is a relationship, and selectivity is a measure of the time or distance between two peaks. So if alpha equals 1, the two peaks have the same retention time and co-elude. Selectivity is defined as a ratio in retention factors. So there are some parameters influencing retention factor: the stationary phase, mobile phase, and the temperature. So I think those three parameters are easy to understand. For example, temperature, the capital K, do you remember? It's CS over CN. It's directly connected with the solubility of one solute. So the solubility is influenced by the temperature. So that's the distribution coefficient. So alpha and K contains the capital K. So those factors also affected by the temperature. And of course, the molecule behavior also will be affected by the stationary phase and the mobile phase, because the molecule will interact with those two phases. So when those two phases change, either of the two phases change, that will change the alpha or K. So because you should use some quantitative way to evaluate your condition, to use those use alpha or K to do some optimization. So you need to. So when you get some numbers, then you think I need to increase K or I need to increase alpha. So what should we do? We should think about some parameters can change these factors. Okay, so let's do some quite simple calculation. So we have a spectrum, and spectrum always. So actually, those we can get many information from spectrum, but actually for the instrument that just simply mirror record the time-dependent signal. We just got the intensity of peaks and the retention time. So from this, let's calculate the retention factor and selectivity factor, also called separation factor. So we can read from the spectrum, we can get the retention time first. So each molecule. And the first peak usually very sharp, maybe not very high, but sometimes it's also quite high. So usually the first sharp peak, the time for unretained stuff. So we got the 2 time point. So from the definition, we can calculate the retention factor. So we can get the 3 retention factor. And then based on the definition, we can calculate the selectivity factors, right? So this calculation usually the starting point when you want to do some more complex or more useful calculation, because this is a starting point. You extract information from the spectrum. So it looks quite simple, but it's very important. So let's see another question. So a small amount of X is injected into a column for length of 40 centimeters. The flow rate of molecule phase is 6.0 centimeter per minute. So what is the velocity of X in the column if the retention factor is 4.0? How long would be required for X to be eluted? So usually when we consider this question, we usually just go back, find the basic definition. So how to resolve this problem? We just go back to here, right? So this is related to the length, the column length, the velocity of mobile phase over the velocity of the solute, and we can get the retention time, and we can get the selectivity factor and the retention factor. So what we should do is just put those on the paper and find how do we get the relationship, right? So here we know we also learned this relationship, right, in the slide. So because we already get the retention factor, so we can start with retention factor from this relationship. So this is the mobile phase, the velocity of the mobile phase. We can calculate the mu, and then we can get the retention time of this solute. So what if the retention factor changes to 4.5? So they're quite simple. We just change the number. Okay, so now we want to we can treat a more complex cases because in this example we can see 2 situations. So in T1 time 1, we know there are 2 solutes, and also there are 2 peaks, but they are not separated very well. And in the T2, they get those 2 solutes get complete separation. So how to describe this using some quantitative way or mathematical way? And from your instinct, we know this one should be the best, right? A very sharp peak and well separation. So this is quite poor resolution. And this one also have a good separation, but the peak is too wide. So in this situation, the middle one, when you panel B, so if you only have two saddles, so that's not a big problem. But if you have many analyzed to be separate, it may cause the column have no enough capacity to separate the multiple analytes. So the best way is panel C. So this is so we need to know how to describe the spectrum and how to control condition to achieve better separation. So we call this line, we call it high efficiency, and this one low efficiency. And one peak, and the panel left to the right, the left one is high selectivity, and this one is low selectivity. You should know why we call efficiency later when in this class. So this is another in terms you should know. Here we more focus on the peak width, and usually we use two definitions of peak width. One is base width. So and another is the width at the half height, the peak width of at the half height of a peak. So this is the half height, and this is the base peak width. So there is a phenomenon. The peak area is fixed, but peak height and width are dependent of retention time. I will explain this in more detail, and this one also related to very important important theory, and we should know how to we would like to avoid this phenomenon, but it's unavoidable. But we want to minimize this phenomenon. So you should know this is always happened. Along the time, the peak will get wider and lower for a certain peak. So because the signal when you measure when you get the spectrum, when using the detector measure it, you just got the usually it's just the concentration related, but the salute could one salute from the starting time to a longer time if the along separation. So there are always some dilution exists. So the total quantity of the analyte is unchanged. So there is no chemical reaction. So if we do not consider the sensitivity of the detector. So we can say the area of the peak is always fixed because the total quantity of an analyte is unchanged. But there's a dilution phenomenon. So the peak width and the peak height is time dependent. Okay, this is a formal definition of the peak peak width at the half maximum. We call it the full width at the half maximum. So this is usually we so this is the formal name. Half maximum. So this is the peak height. So the half height and the full width here. And this is the mathematical relationship between the FWHI and the base the peak the full peak width, the baseline full peak width. This is it's based on the Gaussian distribution. So this is a mathematical relationship. Okay, so in the real spectrum, we always see some peak shape like this, tailing or fronting. So it's because the real world is not always behave like the ideal Gaussian distribution. Sometimes there are some non-equilibrium, and sometimes there is some minor change in the change happen in the stationary phase or the mobile phase, and sometimes it's because of the overloading of your sample. So so that may cause the saturation of the system. So the mobile phase or the station phase cannot dissolve all the sample in a small region. So that causes the deformation of peaks. So this is what we call the overloading. So if the tailing and fronting is not too severe, we can still use we can still treat them Gaussian line. We can still apply those peaks by using the typical using the classical theory, and that's the result to fit the experimental data quite well. So in short, both retention type and the peak width are the main aspect in chromatogram. So the resolution is determined by the average rate of movement of a sample compound along a column. The extent of spreading of the compound while traversing the column. So there's a band broadening. So this show the band broadening more clear. So here we at the initial all the sample inject and enter the column at the same starting point, and And because the two analytes have different properties, so they show different retention behavior. So they have different retention factor. Okay, so those two have certain selectivity factor, and along the separation they can get, and for some for a certain time they can finally achieve complete separation, but because the some dilution behavior exists, I should know. I should say there's some thermodynamic driving force behavior, so that will cause the band broadening, and also the band broadening also contributed by the geometry of column. The band broadening always happen and depend and time dependent, but the area, this one, this one, so this one are always constant. Okay, so now we would like would like have quite sharp peaks. So we need some theory to describe the band broadening and know some factor. We want to know factors and which factor contribute the band broadening and how do we control the band broadening. So we need a theory. So there is, we call the plate theory, and this is and we use the concept derived from the distillation tower. But in the column there's no plate, so we call it a theoretical plate. So it is just an imaginary concept. Okay, but so before that we should know what is the real plate. Okay, single Newton. Spring. No sound. Okay, maybe this video have no sound. This is distillation. So we for the for this chamber, we call this plate geometry. So we call this is a distillation plate, and because this is this chamber, because we distill the liquid, so in a certain chamber, we consider the whole space mixed well. So the whole space have a certain height. So we can also have the concept of the plate height. So this is industrial distillation tower, and we use this concept to measure the efficiency of column. So if we for the real distillation tower, if we have many plates, we should have many more time, many distillation steps. So if we only have one plate, we can only distill one time. So this is a basic concept, and we have another good model. We call the Craig apparatus. I think this one is better than the distillation tower. Okay, so this is okay. This is the picture. So we call this Crick apparatus, and this apparatus is also used to separate two uh, or even for more many more analyze, and by using liquid extraction. So it is a multiple step liquid extraction apparatus. So each unit can do one liquid extraction. So this apparatus have in this picture have 25 units. So this is the structure of one unit. So two immersible liquids mixed in one tube, and one and it can pour into another tube, and this tube will when it flip to the port to this tube, and it flip again, and then the top layer will flow to the next tube. So this so when you stack the tube, the unit, and assemble them to a parallel apparatus, we can do semi-automatic multiple extraction. So when we only consider this one, it's just the one step liquid extraction. So here, this is a simulation program. So we have we have two compounds, A and B. So they have different distribution ratio in the solvent. So let's start. So we mix the A and B together, but they have different distribution coefficient actually. So mix, extract, shake the apparatus, and transfer. So because A in have on 0.5, so this one over this one is 0.5, and B is have 3.5. So this one divided by this one is 3.5. So they have different distribution ratio. And do the next time, and extract again. Repeat it. Repeat. So it's just like the chromatography, right? But they just use the pure liquid extraction. So when we increase extraction steps, we can gradually get the separation. So if we consider the plate concept, so we can consider one extraction tube as one plate. So in this case, we have 19 plates. Right? We have 19 plates. So we can build many a bigger apparatus. So if we have a bigger apparatus, maybe 50 tubes, we may assume we can separate a more complex sample, right? So a higher place for a column can provide more extraction step or more space for the separation. But if the column is too long or too big, even though the column have a higher number of places, but the efficiency is not high enough. So if we have a quite compact apparatus, but the total size is quite compact, but the apparatus still have many plates. That means the plate height, or the size of one plate is small enough, meaning we have very high efficiency. So the plate height, if we say one column have very high efficiency, then meaning the column have a very small plate height. So this is simulation, and we got why we called plate. This is explanation why called plate, because actually there's no plate inside the column. Okay, so here we have the definition. So the plate number, we for a certain column, we have a certain length. Yeah, we got the column length. So the L meaning the length of column. So we have so the H represents the plate height. So the relationship is quite clear. The plate number equals L divided by H, right? So H also H equals L divided by N. So if we get small h for a certain column, certain length of column, then meaning the column have a bigger number of n. Also, it has a better efficiency. So in your textbook, in the textbook, it uses a different symbol when you read the textbook. So you should know it's different from my PowerPoint. The difference just the symbol we use. Note the content. Okay. So the concept of plate height and plate number has geometrical meaning, right? It occupies some certain space if we have the when we consider the distribution tower or the Craig apparatus. But so we also how do we calculate the age in chromatographic column? We use mathematical definition here. So this means we use this one. Okay, this one divided by L equals the age. L also the length of a column, and this represent the space analyzed occupied some certain space in the column. How to say? So when the analyte always you all have some certain amount of the analyte, and those analyte when it goes through the column, it occupies it always occupies some space inside the column. So but we do not treat them from the base point to this base point. We just use we still use Gaussian distribution. We use one standard variation of the peak of the peak and we define this width as a space occupied by one analyte inside the column. So now, based on this definition, we can define the plate height. So, but but even though we have the definition, we still have no way to calculate this. Okay, let's have a 10-minute break and Okay, let's start. Uh, so here you can read plate height is also a quantitative measure of column efficiency. So that's why when we say the spectrum we showed before, that there are high efficiency and low efficiency because uh, so this is why we use the efficiency, but we always add the column before this word. So when we call column efficiency, meaning we are talking about the plate height. So usually we avoid to use the efficiency because this word may cause many confusion. Because we still have time efficiency or some more confusion, confused occasion like separation efficiency. Usually we can still, when we say separation efficiency, we may say the plate height. But sometimes some people also say that the time efficiency, right? So for more clear, we just say the plate height, and when say very exactly the column efficiency. Okay, so this is related to the to length, right? The plate height. So this one also length related quantity. So this is even though we use a standard deviation to define the head pack here. So, but what we can get only time dependent information. But and this chart is no time dependent. So the x-axis here is the length, not the time, right? So we need to build the relationship between time and plate height. So we still need to get time-dependent information. So is this one. The sigma here is also a mathematical definition. It's one standard deviation of peak width when the peak is a Gaussian follows the Gaussian distribution. So the 4 sigma is the base peak width. So this is the peak width at the half height, FWHM. So it equals 2.354 sigma. So this is just the Gaussian definition, Gaussian distribution. So we know this one is related to length quantity, and this is the velocity. So this one divided by this one, we got the time information. So when so this is the time quantity, right? This is time because this is the peak width. Peak width here, how width? It's not some centimeter. How width? The 1 minute. The width is a time quantity. So we connect the two quantity. So the different the basic definition. So we know the full width is the 4 sigma, and then we can do some simple transformation. We should know this one equals this those guys, and in the last slide we can apply that relationship to this expression. We can get h equals LW square over 16 TR square. So TR, we can measure the TR, right? And the width here, we can measure the width directly. It's just also just the time information. And we can know, we of course, we know the length of a column. And use the simple relationship between the plate number and plate height, we can know the plate number is this one. Okay. and we can still represent the W using the SWHM, because sometimes it's very hard to measure the W, but it's quite easy to measure SWHM. That's the reason. Actually, they are they have using this relationship, they have the same result, right? So here, actually, when you see n or h, actually they are the same thing, because they just follow they just related to the L, right? H equals L over n, or n equals L over h. So when we get a larger n, meaning in a certain length of a column, we have many times separation, like many times the extraction unit, like Craig apparatus, or many distillation chamber. So this is the imaginary concept, but because we already defined them, so this concept actually can describe the chromatography, even though the separation process is continuous. So if we have larger n, meaning we have better column efficiency. But when the retention time TR is held constant, peaks with narrow base width, basis peak width will be more efficient than have a, so that also it have a larger n. So otherwise, a column that produce wider peaks will be less efficient, meaning it has a smaller n value. So there is a promise here. We assume they have the TR held constant. Okay, so okay, this is the example, and after this class, I will upload a new version of this PPT and reveal the answer of these examples. So a compound is eluted at 5.0 minutes and have a FW time of 10 seconds. So the column length is 30 meters. What are the value of the number of the reticle plates and the plate height of the column? So try to give you 10 seconds and try to recall the formulas you just learned. Right. Usually this formula is easier to remember, right? But that take a little more time. You can still remember this formula. So we already have FWHM. We want to know the n, so we also have the retention time. So we can apply this formula. So sometimes in the real question, we may know directly say the term like retention time. We just say like this in this example, we say some compound is diluted at 5 minutes. So it meaning the retention time for this compound is 5 minutes. Okay, we use the we should we should transform the minute to the second, because this one is the second, so this is the minute. We don't make mistake here. Right. So we have n, so we and also know the column length, we can get the h. So a larger n corresponding to a smaller h. So what if another compound eluted at 5.6 minutes and have a FWHM of 11 seconds? Right, it's quite easy, the same. Okay. So we already mentioned, and this is a summary. So band broadening is of solid is unavoidable, and it's a problem in chromatography. So this is quite important. It's unavoidable, but we should develop a method to minimize this by this side effects. So this is the core part of developing a chromatographic method. So along the separation, all peak will get broadened. And if the broadening is too severe, we cannot get a well separation. And there's also other problem. Let me go back to this slide. So because they're all along with the separation, we have the band broadening, and a quantity of the solid and it's fixed, so the area is fixed. So if we so if the peak broaden, we just have lower plate height. So if the height is low, it's too low and lower than threshold of the sensitivity of a detector, we have no way to see the analyte. So band broadening not only affect the separation power, also reduce the sensitivity. So because it's unavoidable, so we want to control these side effects, we need to study the mechanism and find a way to develop better methods. So there are three main mechanisms contributing to the band broadening of solids. So one is called eddy diffusion, and we usually call it the A term, and the B term is longitudinal diffusion, and C term we call it resistance to mass transfer. So these three, we divide them to these three mechanism because we can treat these three uh, independently, and each of the term represent a different viewpoint of the band that affect the band broadening, and through study this three mechanism, we can find corresponding method to minimize the effects. Okay, so let's see the A term first, ID diffusion. So here we for the many form of column, we use a packed particle to support the stationary phase. So so here is I use the mouse here. Okay, so here is a packed column, and this is a particle. Now on the surface of the particle is stationary phase, and the space here is filled with the mobile phase. So this is the initial shape of the of an we can consider is the ideal shape of a solid. So after the sample pass through the column, it will get, we will find a band broadening happen. So from the viewpoint of ID diffusion, we would find when we consider the molecule just pass through the particles, okay, but the pathway, the path length of molecules, and because there are many molecules, so the path length, the total path length when the molecule pass through the column are different. So some goes longer path and some goes shorter path. So for example, the molecule 3 goes faster when we only consider the geometry of column, right? This is one one viewpoint, right? So here is the core source of ID diffusion. Okay, when you consider more it in more detail, you will find besides the path length, also the particle shape will affect the path length because there are always some turbulence here. So because there are turbulence that also change the path length. So this one, so this makes this is one term that contributes the peak broadening. So if we use packed column, just from this factor, we should understand the band broadening is unavoidable, right? If we use packed particle to fill the to pack the column, but if we use some open tablet column, so if there's no particle inside the column, so there's no ID diffusion, right? So if you use another form of column, just hallowed open tabular column, so so in that case, there's no ID diffusion. That's correct. But this is depend on the geometry of the column, right? So this term only apply to packed column. And for packed column, this term is unavoidable. So you can consider for a packed column, what should we do to minimize the eddy diffusion? So if we use we can increase the quantity of each particle to make them as uniform as possible, right? If they have a little variation in shape, so they should have a similar turbulent behavior. And if we pack them more tightly, maybe we can reduce the path length distribution. So for some quite tightly packed column, the path length like the green one maybe minimized, right? So they need to, because there's no enough gap between the particles. So this is something we can consider. Okay, now let's discuss term B, longitudinal diffusion. It arises from cellular migration due to concentration gradient. So from this view, we should say for any kind of column, the band broadening is unavoidable. Right. It's because it's driven by the thermodynamic, the second law of the thermodynamics. So we have no way to avoid to eliminate this, but we can still use some way to minimize the effects. Right? So what we can do? So this I think this one is quite easy to understand. So when I say dilution, I previously I usually people can consider that should have some gradient driven dilution, because we can see a peak, so there has some gradient driven force. So what factors may affect this one? Time, right? Time and temperature, not so here, but temperature also affects this one. So usually when you reduce the temperature, using the lower temperature, the diffusion should be relatively low, but in practical, we cannot. Usually, it's not a good idea to reduce the temperature, because that will affect many other property of the separation. So, but you should know temperature will contribute the diffusion rate. So, if the condition allow, we should you can control the top temperature, and more importantly, the time is connected to this diffusion rate, the diffusion extent of this the diffusion. So we usually if the condition allow, we usually apply a fast separation to not let the flow rate, the mobile flow rate of the mobile phase too slow. And this is the third term we call the resistance to mass transfer. So this term is arising from the time need to set up the cellular equilibrium between the mobile and the stationary phases. So in this term, we consider the interface between the mobile phase and the stationary phase. Something on the top, on the surface of the particle. Or for open tabular column, just the interface of the inner wall of the column. So we call here is here there's a word equilibrium. So actually, for if we only consider absolute or the theoretical occasion, we always think everything established equilibrium instant costs no time, right? So, but in the real world, it always costs some time. So, for a certain time, there are always some non-equilibrium process. So in real, like the chromatographic separation, we found the non-equilibrium process contribute the band broadening. So how to let's go back to this. So this one, the term C happened at this region, right? Okay, so now this slide, I want to find okay, I try to write on the slide. So here you can see the stationary phase of this okay. So we can think, so this is a particle, we consider this is a particle. So this is the mobile phase region. So this is the interface, okay? So this is the interface. So ABCD is a time sequence. So any initial, there's a equilibrium, but the mobile phase have direction, right? For example, this one. So for the time one, mobile phase carries the cellulose move forward to the new position. So as this is time 0, okay? So this is the time 0, right? So when we get the time 1, the cellulose in the mobile phase move to this position. So there is non-equilibrium, because if in the equilibrium, the cellulose in the stationary phase should establish the redistribution instantaneously and should have arrived to this position. But actually there's a delay, right? There's a delay. So this is the, still we can consider this is time 1. So they need to re-establish they still need to establish the equilibrium, but there's a delay. When delay happen, so you may say, you may see the time, the band broadening happen. If there's no time delay, the bandwidth should like this, should very sharp, like the time 0. They just move from the position A to position B. But there are some delayed non-equilibrium process. So the time, so the peak width get a little bit broadening. Okay, so This is another chart. If you think the Gaussian-like shape, it's hard to understand. I think the rectangular shape looks easier to understand. So this is a slug. We consider this as a liquid slug, right? So the mobile phase falls, the mobile part move forward a little bit, right? So this is so this one in the settled in dissolved in the stationary phase, still stay in the original position. So this is mechanism. So after the many times extraction or the partition process, the band burning get more severe. So for the actual chromatographic process, any kind of chromatographic process, this also avoidable. So what we should do, we should find some way to help them build equilibrium quicker. So to reduce the band broadening. So resistance to mass transfer lead to slightly non-equilibrium between mobile and stationary phases. So I say when scientists consider the mechanism, they find three independent relationships. So when we sum A, B, C together, and also consider the flow rate of the mobile phase, we have the theory. We called it of the band broadening. We called it the Van Demeter equation. So here we use the H, right, the plate height. So why we consider the mobile phase, the flow rate of a mobile phase? So in term B, we found a time and temperature contributed to affect the term B, but usually we cannot change temperature. So what we should do is to consider the flow rate. And in C, we the mobile phase, the flow rate of a mobile phase also affects the total band broadening. So C multiplied by mu here is it's a relationship. So but for beta, the higher the velocity should reduce this part. Right? So we will find the theta. This part and this part is have some counter effect. So we cannot simply say higher or lower velocity is the best. So they should have some balance point.
石油公司或是北極熊生死。
Okay, so we know we need to find a optimum point. So because their relationship. So this curve is the final point, final result of the Van Demeter equation. We also call it Van Demeter plot. So the y-axis is the h, the phase time. So when we would like to find the lowest point of the phase time. So this reading is the optimum reading. So for each term, so a term is unrelated to the flow rate, right? It only affected by the packing geometry. So the a term is a straight line. So because in here we have the x-axis using the mobile phase velocity. So b term here, we would know if velocity is quite slow, it will induce very severe band broadening. And for C term, it roughly proportional, linear proportional to the flow rate of mobile phase. Right. This is so when we add the three simple lines together, we got this plot. So when you study the HPLC, Dr. Hu will introduce more detail about C term. So, but in my part, we just treat the C term, the C here, as a simple letter. We do not distinguish from CS and CN, but actually the CS and CN contribute this in different mechanisms. Dr. will introduce this. So now, when we know how to measure using a mathematical way, and know some parameters affect the column efficiency, we should know the target. Why we should do this? We want to separate two peaks more efficiently in a single in a certain column. So when we consider two peaks, we still need to measure how well the separation. So we use another concept, the resolution of two peaks. So this is the definition. This is just a definition. So you just need to remember the formula here in the red color. So you should also know if we only have if you cannot get the full width, the width of the base peak, you can still calculate the resolution, right? We can measure the full width at half height, right? So that's not so we do not write the full width at half height form. You also know there are some simple mathematical relationship here. So when you get through the definition, when you get to R equals 0.5, actually what you can see is just the one peak. There's no you cannot distinguish the two analytes. So in theory there are two peaks, but for the detector, through the real data you can only see one the dark the black line here, because the overlapped region they will contribute the total signal. So the height here will flip, will double, so that so the detector so the data you can only see one this dark line. So when you get the resolution equals 1, so this is the ideal peak distribution, and through the detector you can find two well separated peaks. So if you get the one R equals 1, that's good enough. And we define the R equals 1.5 is a complete separation, even though it is not absolute separation. Actually, there's no absolute. So we think this is complete. So here is some example. So sigma is just one standard deviation, right? So when the solution equals 0.5, what we can see is just the dashed line, and this is the solution equals 0.75. So the separation is equals the peak distance is 3 sigma. So one peak distance is 4 sigma. So this 4 sigma is also the width of base peak, right? Base width of the peak. So the resolution equals 1. So when we got 6 sigma separation, we got we call complete separation. So the resolution is 1.5. So we can, if we substitute this equation to the formula, we can build another relationship. So we connect N and R together. So N is another form of column efficiency, the measurement, right? And H actually are the same thing. So we connect column efficiency to R, also the band broadening to the R, right? So this is their relationship. So so most importantly, you should know their relationship follows this mathematical relationship is square root. So R proportional to the square root of N, and not N, right? It linearly proportional to the square root of N. So when we do more mathematical treatment, we can apply K and alpha together to this formula, and we can build the relationship using three factors: the plate number, or the plate height, right? And the retention factor, the selectivity factor. So through this chart, this plot, we can find the relationship among those three factors, how the three factors contribute or affect the resolution. So when let's see the K, the retention factor. So when K is quite small, when you increase K, you can increase resolution dramatically. But when K become bigger, it can contribute, almost as no way to contribute resolution. So usually we just limit, when we develop method, we just limit K smaller than 10. We don't want to, we don't like too big K. One reason is it will contribute the resolution just a little. Another important thing is K is, so this this equation. So if the longer retention time have bigger K, so too big K cannot contribute relationship, but it will cost a lot of time for the separation. So the waste of time and no benefits. So usually we just keep K smaller than 10. So how do we increase the resolution further? So we can find some way to increase N or increase alpha, right? So resolution is the core part of the chromatography, yeah, because it's a separation science. So resolution describes how well to analyze separated. Okay, let's have another break. Okay, let's start. So in summary, we got the fundamental equation. So efficiency. So there are three parts contribute the resolution. One is efficiency, and then the selectivity and the retention part. So selectivity has the highest influence on the resolution. Small changes in selectivity lead to big changes in resolution. So like this, you can find in this picture. So retention has a significant influence at the small k values. And efficiency describes the separation power of the column, and it always have the proportional relationship. So the square root obey the square root relationship, right? They have the linear proportion to R. The square root of n have the linear proportional to R. So here, let's do some exercise. A column has a length of 30 centimeters. The unretained species passes through the column in 1.3 minutes. A and B are allotted at these 2 time point with the peak width at base. So peak width at base, the node at the half height of 1.11 and 1.21 minutes respectively. Calculate the following. Okay, I give you 30 minutes, 30 seconds. Try to find your way to calculate this. Okay, so we got unretained spaces. So this is a TM, and A and B corresponding to TRA and TRB, right? So we just found some, for the question A, we just found some equation could connect with the we known quantities. So here, we're gonna get a theoretical place. So we have the base peak width. So, and we know the TR, we can calculate that. In here, we apply the TRA, right, using peak A. So here, so plate height. So this is quite easy, right? We already have the column length, we can calculate the H plate height, right? So now we can calculate column resolution. Use this definition formula, right? So how? What's a complex one? When if I change the question, if I just ask the question B and do not ask question A, so that will make the problem a little bit difficult. So what you should do is be acquainted with all the fundamental equations. And you can write it down in your draft paper